This is a rewrite of our discussion on the definition of the definite integral. If you remember from 1910, you had the definite integral from a to b of f of x dx. The way people often think about this is that it's just the antiderivative method. If you go back and look at the definition, though, the original definition, you'll find out that it's much more involved than that. Take your interval from x equal a to x equal b, divide it up into n smaller subintervals. We'll call a x0, then we'll have x1, x2, x3, and so on. These x's do not need to be equally spaced. We call such a thing a partition of the interval from a to b. If I is an index, 1, 2, 3, and so on out to n, the subinterval number I ends at x number I and begins at the previous one. The larger number minus the smaller one gives us delta x number I, which is the width of that subinterval. In our work on integration, within each subinterval, we select a number which we'll call ci. This number can be picked as anything in this subinterval, all the way from xi minus 1 up to x number I. In our work at the moment, we will suppose that f is a function with positive function values, at least for the x's that we're interested in. If I evaluate f at some value ci, the vertical height of this roughly rectangularly shaped region will be f evaluated at ci. The delta xi is the horizontal extent of the rectangle. If the function is positive, for example, I could pick a ci so that the function value was 2, and if delta xi was 0.1, the product fci delta xi will be a positive number and will be approximately the area of this rectangle. You have to be careful, though. On the other hand, if the function value is negative, then f at ci times delta xi is a negative number times a positive number, which will be negative. This quantity is not an area then, it's the negative of an area. So, for example, f at ci might be negative 1, delta xi might be 0.1, the product would be negative 0.1. That's not an area because areas can't be negative. Still, presuming for the moment that function f is positive, this sum is the sum of approximations to areas under small chunks of the curve. This sum is approximately the area under the curve when the function's positive. If the function is negative, though, then this sum is not going to represent an area. Each individual terms is approximately the negative of the area of one of those rectangles, so the sum is not the area of this region, it's the negative of the area of that region. In this case, the sum will be negative, not positive. And if the function is sometimes positive and sometimes negative, thinking of the small rectangles that go with region 1, those rectangles will represent areas. So this part, if you just stopped integrating at this point, would be the area of this region. On the other hand, if you continue integrating past this point until the end, that integral is not going to be the area of this region. it'll be the negative of the area. So in this case, the Riemann sum, as you called it back in Calc 1, is approximately the area of region 1 minus the area of region 2. People often say the area above the x-axis minus the area below. Just for notational convenience, we're going to call the norm of the partition the biggest of all of these widths, delta x number I. This gives us an easy way to ensure that the width of each subinterval approaches 0. We'll make the largest of the delta xi's tend to 0, which means they all have to tend to 0. So the limit, as the norm of the partition tends to 0, of these Riemann sums should exist and be equal to the area above minus the area below. If you look in Chapter 4 of the textbook, this limit is defined to be this symbol. Another way of thinking about it is this symbol, which we read definite integral from a to b of f of x with respect to x, is just a shorthand for this limit. Of course, using the limit definition to actually calculate this is unpleasant at best. As an example, let's think about f of x equals x. That is, the way I evaluate the function at a given input is to just give you back the input that you handed me. Since the exact way we select the xi's is not supposed to matter, we'll use a uniform set of points. We'll start at x equals 0 and go to x equal 1. I'm going to divide an interval of length 1 up into n equal-sized subintervals, each one of which will have width 1 over n. So x0 in this case is 0. That's the beginning of the situation. x1 is delta x bigger than that, so that's 1 over n. x2 is delta x bigger than x1, so that's 2 over n, and so on and so forth. I think it's clear that x number I is going to be I multiplied by 1 over n, or I divided by n. Again, I'm supposed to have complete freedom about how I pick these CI numbers within subinterval number I, so totally for convenience sake, I'm going to pick C number I to be the right-hand end of subinterval number I, which is xi, which is I over n. F of x is x, so f of ci is ci, which is I divided by n. When I look at one of these Riemann sums, the function value, f at ci, is I over n. I have to multiply that by delta xi, all of which are equal to 1 over n. So this is the approximation to this integral that we're talking about. Obviously, just looking at this sum, it's the I that changes, not the n. So I can factor two 1 over n's out front, and this is going to be the value of my approximation to the area. There's an algebra fact that was mentioned in Chapter 4. If you do the sum I equals 1 to n of I, it turns out that that's always equal to n times n plus 1 over 2. To look at a specific example, suppose that n equals 4. This algebra fact claims that the sum I equal 1 to 4 of I should be 4, that's the n, multiplied by 5, n plus 1 that is, divided by 2. This would be 20 over 2, which is 10. As a sanity check, though, the sum I equals 1 to 4 of I literally is write down the expression involved, the I, when I is 1, then write down I when I is 2 and 3 and 4 and add them all up. This is 7 plus 3, which is 10. We could do a proof by way of mathematical induction to show that this fact is always true, but you can wait till math reasoning to see that. Before we proceed, we will algebraically simplify these things a little bit. This sum worked out to be 1 over n squared times n plus 1 over 2 because of the algebra fact. You can write a factor of n in the top and bottom to cancel that out. From here, you'll still have a 1 over n. You'll have a 1/2 from the 2 on the denominator, and you still have this n plus 1. If you write the 1/2 out front and then do the distributive law, 1 over n times n is 1, plus 1 over n times 1 is 1 over n. I'm now in a position to take the limit of these Riemann sums as n tends to infinity, which causes delta x to tend to 0. I have to take the limit as n tends to infinity of 1/2 times 1 plus 1 over n. You can take a constant factor out of in front of the limit. As n tends to infinity, 1 over n tends to 0, and 1 is a constant, so it's unchanged by whatever n is doing. This limit is 1/2 times 1 plus 0, which is 1/2 as we expected it to be. Any reasonable person that took Math 1910 is wondering why we didn't just do the antiderivative technique. The antiderivative of x with respect to x is 1/2 x squared. We will evaluate at x equals 0 and x equal 1, do the arithmetic, and get the 1/2 that we got previously without any of this agonizing. Why would you want to do this horrible thing when there's an easier method available? The answer, of course, is that you don't, and we're not going to. Instead, what we're going to do is we're going to take some complicated problem, carve it up into a bunch of very simple problems, like, for instance, our little skinny rectangles. We'll get an approximate answer to the question we're really interested in by adding up the answers from all of the little simple things. Then, to make our approximations exact, we will take the limit as some quantity or the other tends to 0. In the end, this will take the computation that we're interested in and turn it into an integral. Once we've got it like that, we're not going to do the integral by the limit definition. We'll use things like the antiderivative technique. This will allow us to calculate all sorts of things: volumes of revolution, arc length, surface area, work, centers of mass, and time permitting, maybe other things. This is our one big trick of Chapter 7. Approximate things with really nasty looking sums, turn the sum into an integral, and then get your answer from the integral. I hope this discussion has helped people understand what we're up to, and we will see how this goes. Next up, we're going to calculate areas between curves, and after that, we'll begin looking at volumes of revolution. I hope everyone has a good day. I'll talk to you again soon.